Let me welcome you to this lecture. We have now discussed the chemistry of complexes formed by different pi-acid ligands, and during this lecture we will discuss about complexes formed by a sigma donor ligand, that is alkyl ligand. We will discuss the chemistry of uh, metal alkyl complexes. As such, the chemistry of alkyl complexes is of interest because many of these metal alkyl complexes are of biological importance, as well as many metal alkyl complexes serve as intermediate in important catalytic reactions, and we will discuss about all these during our discussion on metal alkyl complexes. So let us now quickly look at the ways how one can prepare metal alkyl complexes or synthesis of metal alkyl complexes. One uses different synthetic strategies for preparation of metal alkyl complexes, and we will discuss these strategies here. So the first or the most popular or the straightforward pathway to prepare metal alkyl complexes is to do reaction of metal salts with alkyl alkyl lithium or alkyl magnesium reagents. That is, one can take metal halides and then do reaction with alkyl lithium or magnesium reagents, which are very commonly used in organometallic chemistry. So one can start with, say, zirconium tetrachloride here, and then do reaction with Grignard's reagent, that is benzyl magnesium halide here. So it will give you zirconium 4. So which is, this compound has a tetrahedral structure that we can draw over here. So this is the structure of this zirconium alkyl complex that can be prepared by reaction of zirconium tetrachloride with benzyl magnesium chloride. So one can also use alkyl lithium reagents. So we can see one example here. So this is dilithiated butane, and if you do reaction with this platinum salt, what you will get this kind of a metallurgical cycle where platinum carbon bond is there, is formed. So this is a metallurgical cycle formed by this alkyl lithium reagent. When it was reacted with this platinum complex, we obtain this metallurgical cycle with metal alkyl bonding. So these alkyl lithium or alkyl magnesium reagents essentially provide us with carbon ions, and these carbon ions are strongly carbon ionic, and therefore we can replace all the halide counter ions present in the precursor complex, and we end up with a product where there is no halide is left. But we can also use other main group element alkyl reagents, and these reagents will essentially allow us to replace few of the halide ligands instead of all the halide ligands, so we can control the reaction and then replace do substitution or replace some of the halide ions by using these other main group alkyl reagents. So main group alkyls. So examples are aluminium, say zinc. You can also take lead or tin alkyl reagents and then do reaction with metal halide to obtain partially alkylated metal alkyl complexes. So we will see examples. So if you take titanium tetrachloride and then do reaction with Al2 Me6, so we will be able to replace one of the chloride here by a methyl group, and then MeTiCl3 is formed. Similarly, if you take niobium pentachloride and then do reaction with dimethyl zinc, again you will be able to replace two of the halides here, and then Me2 niobium Cl3 is formed. So we can control the reaction by using these main group metal alkyls instead of lithium or magnesium alkyls, and thereby isolate products where not all the halide ions are replaced by the alkyl groups. So the second method of preparation of metal alkyls involve essentially reaction of metal hydrides with olefins. So we can take metal hydrides and then do reaction with olefins. So you can take this platinum complex and then do reaction with ethene. There will be insertion of the olefin onto this metal hydride bond here, and what we will obtain as a product here again is a metal alkyl in this way. So we see how the olefin gets inserted into the metal hydride bond, and this sort of reaction, or this reaction where an olefin gets inserted into a metal hydride bond, essentially again is important in isomerization of olefin reaction. So this particular step is an important step in the catalysis for isomerization of olefins. We can also use dienes here. So reaction of metal hydride compound with diene, that is say butadiene here, will give us metal alkyl So in this case, we will end up with this sort of a compound after this butadiene is reacted with this iron hydride complex. Essentially, we end up with this sort of metal alkyl complex. So this is another strategy for preparation of metal alkyl, that is reaction of metal hydrides with olefins. So one can also do reaction of metal hydrides with carbenes to prepare metal alkyls. We'll see one example where a molybdenum hydride complex upon reaction with carbene, that is say diazomethane here, will give us a metal alkyl complex in a very straightforward way, in this way. Then another synthetic route for preparation of metal alkyls we have already seen during our discussion on reactivity of metal carbonyls or metal carbonyl anions essentially. So that is, we know the reaction of metal carbonyl anions with alkyl halides give us metal alkyls. We have seen one reaction where Mn2CO10, which upon reduction with sodium gave us a metal carbonyl anion, that is in this way, and this upon reaction with alkyl halide we obtain alkylated compound in this way. We have also seen that instead of alkyl halide, if we use acyl halides, then we obtain the corresponding acylated product. So (13, 14, 15, 14, 15, this is 8, so 8 plus 5, 13, 13 plus 4, 17. So this is negatively charged complex, not positively charged complex. And then only we can get an 18 electron complex because. So this upon acylation will give us acylated product here, metal carbonyl anion again. Now, this acylated metal carbonyl complexes essentially, if we do photoirradiation or if you heat it, then it decomposes and releases carbon monoxide to give us alkylated compounds in this way. So we can obtain the metal alkyl complex from the metal acyl complex by photoirradiation or by heating the compound when the release of carbon monoxide takes place, and we obtain this metal alkyl complex in this way. So reaction of metal carbonyl anions with both alkyl halides and as well as acyl halides essentially gives us metal alkyl compounds in this way. So another synthetic strategy that involves that yields these metal alkyl complexes involves reaction of a 16 valence electron species with alkyl halides. So that is the fifth route, 16 valence electron complex with alkyl halides. So we know these D10 or D8 metal complexes, the square planar complexes are essentially, they get stabilized in 16 electron complexes are stable, such complexes, that is D10 as well as D8 square planar complexes. And to such complexes we can add alkyl halides or and then we can obtain metal alkyl complexes essentially. So let us take a 16 electron D10 complex here. So that is contains a olefin ligand in this way. So the platinum center 10 electrons are there and 4 electrons from the 2 phosphine ligands, while this olefin ligand here is a 2 electron donor. So this complex is a 16 electron species essentially. So then one can do reaction with alkyl halide. What is going to happen here? The oxidation state of platinum is equal to 0, and now the oxidation state of platinum is going to increase, and it will also increase its coordination number. That is draw balls in this way. So now the oxidation state of the platinum center has increased and it has become a +2, and the coordination number also from earlier coordination number 3, now it has the coordination number is equal to 5 now. And this sort of reaction where the metal essentially increases the coordination number as well as it gets oxidized, we call such a reaction as oxidative addition reaction. Also, here what we should notice is that the oxidative addition has taken place in a cis fashion because the two ligands that comes from this methyl iodide both are cis to each other. So the addition has taken place in a cis fashion. And now, upon heating, the olefin is going to be released. It is and we will end up with a square planar complex in this way. So just by reaction of alkyl halide with this, or oxidative addition of alkyl halide to this 16 valence electron precursor complex, we obtained a metal alkyl complex here. And in this case, now here again, if you count the number of electrons, you will find it is 16 valence electron species, while this particular species is an 18 valence electron. The intermediate complex is 18 valence electron, while the product here is a 16 valence electron species, as both methyl and iodide are 1 electron donor essentially. Phosphine is 2 electron donor, and there are 10 electrons from platinum, 4 electrons from the 2 phosphines, 1 electron from both methyl and iodide ligand, and that is equal to 16 valence electron species. So this is a very prominent route for preparation of metal alkyl complexes, that is by addition of alkyl halide to 16 valence electron species. Now in this case we have seen that the oxidative addition takes place by in a cis fashion. We also have examples where oxidative addition takes place in a trans fashion. So let's see such an example. take the viscous complex here and then do reaction with an alkyl halide here. So iridium is in +1 oxidation state in this compound, and now oxidative addition will take place in transformation as the two incoming ligands are trans to each other. So the methyl and the chlorine here are both trans to each other, and your oxidation number of iridium has increased from +1 to +3 in this case. So we obtain the metal alkyl again by oxidative addition of metal halide with a 16 valence electron. This is 16 valence electron species. Addition of this methyl chloride with this 16 valence electron iridium complex here. So such oxidative addition can take place even in case of 18 valence electron species, provided the metal center is strongly basic or the metal is in low oxidation state, that is this is neutral actually. So upon addition of methyl iodide, oxidation of the metal center takes place and also the coordination number increases. And the methyl groups comes and gets attached to the cobalt center in this way. So the cobalt now has a oxidation state of +3 as the Cp is negatively charged as well as the methyl group is negatively charged. So there will be a plus charge on the complex ion here, and iodide is a counter anion here. So again, if you count the number of, this is for the precursor complex. Now if you count the number of electrons, what you will find, cobalt is a D9 metal center. So 9 electrons from cobalt, 5 electrons from the Cp ligand, 2 electrons from carbonyl as well as 2 electrons from the phosphine ligand. So this is equal to 9 plus 4, 9 plus 5, 14 plus 4, 18 valence electron. So the precursor complex is 18 valence electron species, unlike it is not a 16 valence electron species, and oxidative addition can take place now even in an 18 valence electron species, since the cobalt ion is in low oxidation state here, it is in +1 oxidation state, and that is why it is prone to undergo oxidation, and methyl iodide can now be added in this way, so that oxidation number of cobalt has now increased from +1 to +3, and now a very interesting reaction takes place, that we call methyl migration reaction. That is, the iodide now gets attached to the metal center, PPH3 is intact, while the methyl groups migrate to the carbonyl group, towards the carbonyl group, and in this way it forms an acylated product now instead of a metal carbonyl complex. Now this is a metal acyl complex, and the oxidation number still remains, of course, +3, because again the acyl group is negatively charged, iodide is negatively charged, and Cp is again negatively charged, and the entire complex is electroneutral. So what we have seen here is that oxidative addition can take place even in 18 valence electron species to eventually give us this metal alkyl complex. But such metal alkyl complexes with carbonyl ligand here are prone to undergo this methyl migration reaction, and that will eventually give us metal acyl complexes. You will learn more about this methyl migration reaction or the mechanism of this methyl migration reaction during your discussion on organometallic analysis. So there is another route for preparation of metal alkyls, that is nucleophilic addition to olefin complexes. So when we have a metal olefin complex, say here nickel cyclooctadiene complex, this nickel cyclooctadiene complex here, and it is positively charged because 8 electrons from nickel here, 5 electrons from Cp, and because it is a diene ligand, it is a 4 electron donor, and so then we have to deduct one charge, one electron because of the positive charge here, and what we get is a 16 valence electron species over here. So nucleophilic addition can now take place to the olefin part of this complex here, and if you do reaction with the nucleophiles, say methoxide here, then it can come and attack on one of the olefin here, and this will essentially give us because one of the double bond will get saturated now, and nickel will get attached to now a sp3 carbon atom here, that is formed after attack of the nucleophile on one of the olefin in this way. So both the carbon atoms become sp3 instead of sp2 now, and one of the sp3 carbon atom is now attached to the nickel center in this way. So now again the positive charge is gone, and again what you will find here, the number of electrons, 8 electrons from nickel, 5 electrons from the Cp ligand, 2 electrons from one of the olefin, and 1 electron from this alkyl group over here, and this will be equal to 8 plus 5, 13 plus 2, 50 plus 1 equal to 16 valence electrons. So once again we end up with a 16 valence electron species in this way. By attack of this nucleophile on this olefin complex, we convert one of the olefin bond into sp3 hybridized carbon atoms, and then one of the sp3 hybridized carbon atom will get attached to the nickel, and that we will get a metal alkyl complex in this way. So this essentially brings us to the end of this lecture, and we learned about the preparation of metal alkyl complexes. During this lecture, we have seen that there are several methods for preparation of metal alkyl complexes. Initially we discussed about the reaction of metals halides with alkyl lithium or alkyl magnesium reagents to produce metal alkyl complexes, and then we saw one can also use other main group metal alkyl reagents like aluminum alkyls or zinc alkyls or say lead alkyls as well as tin alkyls to produce transition metal alkyl complexes by reaction with appropriate transition metal salts. And these reagents have the benefit that they can be used for replacing some of the halide ligands instead of all the halide ligands. So we end up with metal alkyl halides when we use these main group uh, alkyl reagents essentially. And then the second reaction that we discussed for preparation of metal alkyl is the reaction of metal hydrides with olefins. We saw that the olefin can get inserted into a metal hydride bond, and that in this way it can lead to the preparation of metal alkyls. And we also discussed that such reactions are of importance in the catalysis of olefin isomerization. That is, during the olefin isomerization, such insertion of olefins to metal hydrides essentially take place. And then the third reaction for preparation of metal alkyl we discussed was the reaction of metal hydrides with carbenes, and again we saw one example of preparation of metal alkyls by following this particular route. The third route that we discussed for preparation of metal alkyls was discussed during our discussion on the reactivity of carbonyl metalates. That is, the reaction of carbonyl metalates with alkyl halides will give us metal alkyls, or we also saw that the reaction of metal carbonyl anions with acyl halides also eventually give us the metal alkyls upon irradiation or upon photoirradiation or thermal decomposition of the acylated products essentially give us the metal alkyl compounds after release of carbon monoxide. And the next reaction that we discussed about preparation of metal alkyls was the addition of alkyl halides to 16 valence electron species, and we saw that how one can add alkyl halides to different 16 valence electron species to produce metal alkyl compounds. And we discussed about oxidative addition of these alkyl halides to different 16 valence electron species, and we saw that both cis addition as well as cis oxidative addition as well as trans oxidative addition can take place depending upon the complex. And also we have seen that such oxidative addition reactions are possible even in 18 valence electron species where the metal center is strongly basic in nature, that is, the metal center is in low oxidation state. And then the last reaction that we discussed for preparation of metal alkyls was the reaction of metal olefin complexes with different nucleophiles that gives us metal alkyl complexes. So with this, let me conclude this lecture. I thank you very much for being with me during this lecture.